Welcome back to Chem Talks, guys. On today's podcast, which is our last one of the gas laws, we are going to talk about a situation, first of all, where we have two variables changing. When we talked about Charles and Boyle's and Guy-Lussac's law, we only had one variable changing. Today we're going to talk about what happens when we have two variables within a problem changing. And then in the second part, when we talk about the ideal gas law, we're going to bring in the concept of how much gas do we have and how does that affect it as far as the number of moles. So let's go ahead and get started by talking about the combined gas laws. We use the combined gas laws when both temperature and pressure are changing in the same problem. If you remember back, temperature and pressure were Charles and Boyle's law. So combined gas law basically means we're combining Charles and Boyle's law. And it looks something like this. P1V1, so pressure 1, volume 1 divided by temperature 1 is equal to your second pressure times your second volume divided by your temperature. And the key with these problems is we have 6 variables. You're going to be given generally 5 of these, and you have to solve for one. So you're going to have to algebraically rearrange this equation. Hopefully by this time in the semester you know how to do this. If not, come see me and we will teach you how to do this. But let's go ahead and do a couple problems and show you how we do rearrange these. So problem number 1 here says a gas occupies 15 liters at 800 torr, 96 degrees Celsius. What would be its volume at 0.93 atmospheres and 68 degrees Celsius? So a couple things I noticed right away. My temperature is in degrees Celsius, so I'm going to have to convert that to Kelvin, right? I had 273 to those. And if I look at my atmospheres, I have one is going to be in torr, the other one is going to be atmosphere. So we're going to have to go to either atmospheres or torrs. For this problem, I'm going to go to torrs. Remember that 1 atmosphere is equal to 760 torrs. So my equation is P1V1 over T1 equals P2V2 over T2. Now I'm solving for this V2. So when I rearrange it to solve for V2, it looks something like this. V2 is equal to P1V1 times T2 divided by T1 times P2. So I set up my original one. You'll notice that the 0.93 atmosphere, when I convert it, became 706.8 torr. Okay. Now I'm going to have to basically take this times this, cross multiply, and then take this times this, and then divide. So I get an answer of 15.69. So originally started off with 15 liters, and now we slightly increase. Right? Let's try another problem here. A gas occupies 42.3 milliliters at 24 degrees Celsius and 725 millimeters of mercury. What will be the volume of this gas at 12 degrees Celsius and 750 millimeters of mercury? Go ahead, pause the video, try this one on your own, then come back. Alright, now that you've done it on your own, if you haven't, stop, don't cheat, do this as I always tell you. First thing I notice, once again, we have our temperatures in Celsius, I have to convert them. My volumes are the same, so I'm doing pretty good. It doesn't ask what volume I want, so I'm just going to keep it in milliliters. So I'm going to use the combined gas law equation then, and I'm going to be solving for V2, kind of like we rearranged it in problem number 1. So I set it up this, okay, and I'm going to solve for V2. So I kind of cross multiply and divide. You can think of it that way. Okay, and I get an answer of 39.24 milliliters. Hopefully you got that as well. So pretty easy. We could do this for temperature as well, where we'd solve for T2 or any of those variables. You just have to know how to rearrange this. If you're having problems, please come see me. All right, our second type of problem for today is takes into what we call the ideal gas law. And ideal gas law is going to relate multiple factors. It's going to relate pressure, volume, temperature, and then something new that we haven't put in yet, and that's the number of moles to an ideal gas. Remember in our intro to gas video, an ideal gas follows all the gas laws perfectly. Kinetic molecular theory means we have totally elastic collisions with each other. We're not losing or transferring any energy, and also there's no intermolecular attractive forces between the gases. The ideal gas law says this: PV equals nRT. Well, P is pressure, V is volume, N represents the number of moles. So you might have to convert from grams to moles, and you guys know how to do that. R is what we call the gas constant, and you will need to know this value along with its unit. So R is equal to 0.82 liters times atmosphere over moles degree Kelvin. Okay, and then T is temperature. A couple things to notice about this value here. Atmospheres are units. So when we do the pressure on the other side, it has to be in atmospheres. Temperature we know is always in Kelvin as well. Okay, or volume is always in Kelvin, and then volume is always in liters. It's really important that you set this up right. That way when we do our factor labeling and dimensional analysis, everything will factor out. So let's try a problem. What is the volume occupied by 0.54 moles of N2 gas, nitrogen gas, at 15 degrees Celsius in 0.97 atmosphere? Well, PV equals nRT. So pressure I have, what's my pressure on here? I got 0.97 atmosphere. That's what we want to use it. We have moles, we know our N. We know temperature 15 degrees Celsius, but we got to add 273 to get that in Kelvin, so we're solving for V. Okay, so I set it up like I have here. Now if I want to get V by itself, I'm going to divide the right-hand side by P. So V equals nRT, number of moles, times your gas constant, times temperature divided by P. So when I rewrite this out, here's my moles, 0.54, my R, 0.082 liters times atmosphere per means put on the bottom, moles per Kelvin. Okay, T is 288 kelvins. And then P was given at 0.97. Notice when I do this, my kelvins cancel out there, my atmospheres, and then my moles cancel out, so I'm left with liters, and I get an answer of 13.19 liters. Okay, problem number 2. Copy this down and try this on your own. Once you get it done, come back and see me. So it's pretty easy, I think, for you. All right, hopefully you've done this and didn't cheat. If you cheated, stop. I know I tell you this every time, but it's not going to do you any good just to write the answer down. You got to work the problem. So once again, PV equals nRT. What do we have up here? Well, we have volume. Okay. We have temperature. Once we convert it, we have atmosphere, and we're trying to find N. We're trying to find moles. So if we set it up like this, we're trying to solve for N. So N is going to be equal to P times V divided by RT. So rearrange this. I have 63.3 atmospheres times 10.3 liters divided by 0.082 liters per mole Kelvin times 294. Now, if I were to write this correctly, I would actually put the moles per Kelvin up top to do it mathematically, but in this case I'm writing this. This way, let's see, we have our kelvins. This would be up top. It's canceling out. Our atmospheres cancel out. And I will be left with moles. So when I do this mathematically, I end up with 27.04 moles of chlorine gas. So pretty simple. All right, guys. Pretty simple podcast today. We learned the combined gas law and the ideal gas law. Only trick is, remember, we got to make sure we're using the correct units in these, and make sure you know the units for the gas constant and know how to write those down. Once again, guys, if you're having any problems rearranging these, we arrange mainly for volume. Okay, we did one for an ideal gas law for moles, but if you're not sure how to rearrange those, please come see me. I will help you with those. If you're having problems, also you can go down to the RTI room and get help with the math tutor. They will help you as well, but probably quick and easy. Just come into me. All right, guys, so until next time, take care, and I'll see you in class. Bye.